Hi, my name is Tom Goodwin, and I'm currently a sophomore chemical engineering student. I will be presenting about membranes for separations. So, what do separations do? In general, they remove any unwanted substances from a system and purify important substances. This can be anything from removing contaminants from your drinking water to purifying gasoline for your car. Why are separations so important? Separations are found in numerous applications, like the ones I just mentioned, and are only becoming more important. As we all know, pollution is a huge issue, and we are in dire need of solutions to remediating the environment and stopping future pollution. Separations technologies can be used to remove these pollutants from air and water emissions, which is very promising. So what are some different separation processes that can be used for air and water systems? One type is distillation, which separates vapors and liquids by heating mixtures to a temperature below the boiling point of one substance and higher than the other. While it is very effective for some substances, it often requires high amounts of energy and can only be used for specific separations. Another type is adsorption. Impurities in a mixture deposit into a highly affinitive surface, while the rest of the mixture is not attracted and flows on. The downside to this process is that those impurities have to be removed from that surface, so it's usually discontinuous and requires a desorbing process. Extraction is also a popular separation process. Impure liquid is combined with another immiscible liquid that dissolves the impurities from the impure liquid. This process is usually also discontinuous and requires a high supply of immiscible liquid, which is usually specific to the desired liquid. So it's not super efficient. So all of these processes are good in their own individual specific applications, but they can't be used for that many different applications. Membranes, however, can achieve all these processes while being able to do so continuously and very efficiently. So membranes are ideal for the separations we are doing. So what are membranes? They are a discrete thin interface that moderates the permeation of a chemical species in contact with it. So in other words, membranes are like nets that stop some substances from passing through while letting others flow through freely. Some parameters of membranes include pore size, which mainly determines what is allowed to pass through the membrane. This diagram at the bottom right shows how different types of filtration relate to this pore size of those membranes. Conventional filtration has the largest pore size and is the most common type of filtration here. As pore size begins to get smaller, the more selective these membranes get. Reverse osmosis, with the smallest pore size, deals with separating salt from water, which shows how selective these membranes are. Other parameters are material, fiber width, which plays a big role in flux, which is the rate at which a gas or liquid passes through the membrane, and gradient or charge, which helps specify what substances are able to permeate the membrane. Our lab mainly uses polymer ultrafiltration membranes in pressure-driven systems. So this is how our membranes compare to other membranes in terms of pore size. So why do we use membranes? Well, a key property of membranes is their ability to selectively control the permeation rate of chemical species through the membrane. This characteristic allows for high energy and process efficiency, high product quality, which means high purity, and usually membranes can be implemented simply and combined with other processes to achieve multiple goals. Some specific applications of membranes are separating components of a mixture, like removing salt from water or removing larger particles like bacteria, regulation drug delivery from a reservoir to a patient, and membranes are even being used to produce artificial kidneys and lungs now. So all of these applications are very important, just showing why membranes are so useful and important. So the main issue with membranes is fouling, which contaminates and clogs the membrane. Types of fouling are high concentration near the surface. Since these particles are not allowed through the membrane, they often build up in concentration near the surface, which decreases the number of desired particles in contact with the membrane. Another is the formation of a cake layer. Particles are also can also become attached to the surface of the membrane, forming a layer that blocks the surface and prevents any particles from coming in contact with the membrane. Another kind of fouling is pore blockage. When a larger particle makes its way into the membrane partially, but gets lodged in, it blocks that singular pore for any other particles trying to pass through, resulting in reduced permeation. A similar mechanism is adsorption of foulants. When particles permeate the surface, but are also attracted to the membrane, they can deposit on the surface of some fibers in the membrane, which decreases pore size and permeation. So all these types of fouling make a membrane much less efficient over time. So one possible solution to reduce fouling of membranes is biomimicking the pitcher plant. Pitcher plants secrete a lubricant type of liquid on their surface to make it more slippery. The picture on the left shows a dry surface pitcher plant where ants can crawl all over it with ease. After lubricating its surface, all ants that try and crawl in the pitcher plant fall in very quickly, as seen on the right. Mimicking this technique, we get slips, slippery, liquid infused porous surfaces, which may be a solution to membrane fouling. So how do we prepare a membrane for filtration? To start, we use Thermo Fisher Scientific PVDF membranes packaged in rolls soaked in glycerol. We first begin by placing the membrane in isopropyl alcohol for 30 minutes, then rinse 3 times with deionized water and place the membrane in water for 24 hours. This removes the glycerol from the membrane. Next, the membrane is cut to size so it can fit in the compartment. And finally, the membrane undergoes a compaction process with water to finish the preparation. The end result, a compacted, rinsed, shaped membrane ready for filtration. Dead-end filtration is a common type of filtration used in laboratory experiments. The feed is perpendicular to the membrane, allowing only permeate to pass through, while the retained particles collect at the surface of the membrane. Obviously, this results in fouling of the membrane, so this type of flow is often used for experiments to test maximum fouling of a membrane. The picture on the right depicts our dead-end system that our lab uses. The nitrogen cylinder supplies pressure to the feed tank, which pushes feed through this tube at the desired pressure. The feed travels along to the dead-end filtration unit, which houses the membrane and where the separation occurs. After that, permeate collects in this tube and passes into this bottle where it collects. So compaction basically condenses a new membrane down so that the flux is constant. We do compaction in our dead-end system using water as the feed so the membrane isn't fouled. The membrane is subject to feed at 3 bar pressure for 2.5 minutes. Then the process is paused to measure the volume of water collected. The process is continued until the volume of water collected is within 5% of the volume of water previously collected. The graph shows that after about 30 minutes, the data begins to plateau, so the membrane is compacted, meaning that the amount of water passing through the membrane doesn't change with time anymore. So, as I mentioned earlier, lubricating a membrane like the pitcher plant could be very effective and have many anti-fouling properties. So, but the other side of that is that it has to have certain characteristics to work properly. It must completely absorb and stably bind to the membrane so it covers all porous surfaces. The lubricant and the liquid being filtered must be immiscible so the lubricant stays pure on the membrane. And finally, the binding of the lubricant to the membrane must be more energetically favorable than the liquid being filtered binding to the membrane. So the lubricant isn't washed off the membrane and isn't lost at all. So it constantly stays there. With these characteristics, a membrane would gain many anti-fouling properties and increase its lifetime by a lot. So what's next? There are many different tests we can do on the lubricated membranes. Determining what lubricants work best on the membranes we use will be important, like plant oils versus synthetic lubricants. Testing with different feeds will also be key to understanding more about the SLIP's properties. Cross-flow filtration is also something to research more about. Since the flow is parallel to the surface of the membrane, the tangential flow carries the feed across and the retentate to an outlet stream, while the permeate passes through the membrane. So since the retentate doesn't build up on the surface of the membrane, it has much more anti-fouling properties and the membrane lasts much longer. Researching these anti-fouling solutions will be beneficial to all membrane processes and is very promising for separations. Thank you for your time.